So our next speaker is Ms. Namrata Bansal. She is currently working at Karlsruhe Institute of Technology, Germany. And the title of her talk is Observation of Magnetic Skyrmions in Fe3GeTe2 using spin-polarized scanning tunneling microscopy. And I think she is also an alumnus of IIT Delhi. So with this, yeah, Namrata, please go ahead with your presentation.
Am I audible to everyone?
Yeah, not properly, but yeah, you can a little bit raise your voice or maybe raise your volume.
Now is it fine?
Yeah, I think you can start.
Okay. Thank you very much for the nice introduction. So, a very warm greetings to everyone. I am Namrata Bansal. First of all, I would like to congratulate Professor Mutli for completing 10 years of SPINTRONICS in IIT Delhi. And I would like to thank for inviting me here and giving me this platform to speak here and giving me the chance to present my ongoing PhD work. So I did my master's from IIT Delhi in the batch 2020, that is the COVID batch. I did my master thesis on crack-MOOC magnetometry to quantify the interfacial DMI on graphene NIFE system. So now I will start with my PhD ongoing work. Okay, so I'm doing my PhD under the group of Professor Wolfheckel from Karlsruhe Institute of Technology, Germany. I would like to thank my STM experiment team for the coordination during the ongoing experiment. I would like to thank my theory team for providing us our DFT calculation. And I would like to thank our crystal core for providing us a very nice samples. So the topic of my presentation is observation of magnetic skyrmions in iron germanium telluride, which is also known as FGTE, using spin polarized scanning tunneling microscopy. So I will start with the crystal structure of FGT. So FGT consists of two types of iron atoms, that is iron 1 and iron 2. So iron 1 atom makes a hexagonal network with the other iron atoms, while iron 2 atoms make a covalent bond with the germanium atom. Now these together are separated by two tellurium atom by weak van der Waals forces, and hence one unit cell of FGT is prepared. Now if I talk about the properties of FGT, it's a quasi two-dimensional ferromagnetic van der Waals semi-metal. Its Curie temperature is quite high as compared to other materials, which is 205 Kelvin. It's known for hosting skyrmions. It has an inversion symmetry due to which there is no DMI, and it has a large perpendicular magnetic anisotropy. Now I will talk about the characterization technique which we have used in this work, which is spin polarized scanning tunneling microscopy, which is also known as SPSTM. So in this technique, what happens, the spin polarized tunneling current tunnels from magnetic tip to the magnetic sample, which depends on two factors. First is the relative alignment of the local magnetization of tip and sample, and second is the spin polarization of tip and sample. Now what happened due to the tunneling magnetoresistance effect, when the two spin state of the tip and the sample is in parallel condition, then what happens, the differential conductance, which is proportional to the local density of state, is much higher as compared to the anti-parallel case. Now the application part of the SPSTM is, it's a very nice tool for probing electronic and magnetic property at nanoscale. It is very useful for extracting the micromagnetic properties such as domain wall width at high lateral resolution. We can also determine the value of differential tunneling conductance at various range of magnetic field. So in this work, we have used a tungsten tip, which was coated with 50 monolayers of chromium, which is an antiferromagnetic material, in order to avoid any stray field effects during the measurement. Now I will discuss about the experimental part. So in this work, we have used bulk crystal of FGT, which was around 200 micrometer thick. So it was cleaved in situ and under the condition of ultra high vacuum at room temperature. Thereafter, after cleaving, it was directly transferred to the STM, and the temperature of STM was 0.7 Kelvin. Now we'll discuss the first measurement results. So we found during the scanning this mapping in DIDV maps. So this is at zero field on the middle one. Now to confirm whether this is a magnetic contrast or something else, so we apply magnetic field in two directions, that is in the negative and the positive direction. But we found that in the negative direction, these magnetic contrasts are shrinking, while on the positive side, it was expanding. So these white arrows are showing how these magnetic contrast is expanding towards the positive magnetic field direction. So this expansion of the magnetic feature is the clear proof that our tip is spin polarized in the out of plane magnetization. Now, after confirming that our tip is spin polarized, so we proceed to the next level of experiments. So what we did here, we took the DIDV spectroscopy on the dark domain and the bright domain. So the purpose of doing this was to get the information of the spin polarization of the electronic state of FGT. So what we found here that when we tried the spectroscopy on the down domain, so we found, which is indicated by the blue line, we shows a height in the curve. And for the up domain, which is showing in black, it shows a dip at the Fermi level. Now to see the behavior of this, so we found that they are reacting opposite nature from the bias value of minus 200 millivolts to around positive 200 millivolts. So to confirm this behavior, we tried differential DIDV mappings at different range of applied bias from minus 500 millivolts to 500 millivolts. So what we have observed here that the magnetic contrast at minus 500 millivolt and 500 millivolts is almost similar. Now, if we go towards the lower value of bias value, what we have observed that this magnetic contrast is decreasing, and at minus 200 millivolts, it starts reversing its contrast from dark to the light. Which is in a good agreement with what we have found in our spin polarized spectroscopy. Now, if we talk about the dip, what is the reason behind the dip? It could be due to the inelastic excitation of the spin wave, which is also known as magnon. But in this work, we have not considered any magnon effect further. Now, in this part, I will compare the spin polarized spectroscopy with our DFT calculation on two opposite magnetic domains. In DFT calculation, we have only considered 3 layers of FGT, and we do not consider any type of interaction or inelastic excitation. So we can clearly see that it is not resembling with our experimental data. But here we can observe that the down domain and the up domain are showing a same trend as they are showing in the experimental data. So here we can say that the DFT calculations are in qualitative agreement with the spin polarized STS. Now, as we have already talked about the magnetic bubbles, now for our curiosity, so we went to the zoom-in portion of these magnetic bubbles, which we have found, and we reached up to the level of domain wall boundary. And this is a very small scan at around 30 nanometer by 50 nanometer. So we did the spectroscopy along this line, as you can see it from blue to the dark. And what we have observed in the spectroscopy, that the transition from one type of domain to the other type domain is very smooth, and there is no additional state occur during this spectroscopy, which explains that there is no additional electronic states created in the domain walls. Now we have already reached to the domain wall boundary range. We try to calculate other properties such as domain wall width and exchange stiffness. So I will start with the domain wall width calculation. So in this experiment work, we have taken a very small area of domain wall boundary, and we applied two different biases, that is 500 millivolts and minus 500 millivolts. And we so this is a wall profile of domain wall width in A and B at two different biases. So what we have observed here that the forward and backward are coinciding in both the cases, which explains that there is no interaction between the tip and the magnetic domain walls, so that there is no shift in during the scanning, which is a very nice thing. And we this red thing is average profile fitting, which is calculated by taking the 10 hyperbolic, and we can calculate the value of domain wall width here. Now the behavior of this domain wall width is similar to the block wall, as we can see that the fit nicely reproduce the shape of the domain wall. Now we have a relation which is proportional to the 10 hyperbolic. So using this equation, we can easily calculate the value of domain wall width, which is around 7.11 nanometer and 7.32 nanometer, and which is almost same at two different biases. So we can say that the domain wall width is not much dependent on the applied bias direction. Now we have a DFT calculation from which we have also calculated the value of domain wall width, which is around 5 to 6.3 nanometer, and it's closely matches with our experimental value. Now I will talk about the second part, that is the exchange stiffness calculations. So the domain wall width contains the information of exchange stiffness and anisotropy constant. Now we have this relation. So from the squid measurement, we have a value of anisotropy constant, and we already calculated the value of domain wall width, which is at 7 nanometer. If we put these two values in this equation, we can easily calculate the value of exchange stiffness. So from the DFT calculation, we also calculated the value of exchange stiffness, which was very much closely matches with the experimental value. So the domain wall width and the exchange stiffness are in good agreement with our DFT calculations. Now I will talk about the skyrmions, which is the most important and interesting part of this experimental work. So we have already gathered all the values which is required to make a nice recipe of skyrmions. So now I will explain how these skyrmions are depending on the applied external magnetic field. So it starts from the very low value of magnetic field. As you can see here, that this random shape of the magnetic feature is shrinking towards the higher magnetic field value. So if we go more higher value in the negative direction, we can observe that this random shape is changing into an elliptical shape, which is a stabilized shape. And then if we go further to the external magnetic field, we observe that this stabilized oval shape changes to a very stable state to the circular shape. And hence these skyrmions are becoming very small. So we need to change our scan area to see a very nice resolution of these skyrmions. And thereafter we applied again an external magnetic field, and we have observed that these skyrmions are keep on shrinking, and at certain value of magnetic field, it disappeared or vanished. Now the question arises, why these skyrmions annihilate? So there could be two possibilities. First is the skyrmions with DMI and skyrmions without DMI. Now I will first discuss the skyrmions with DMI. So what, as we already know, the skyrmions are, a skyrmionic radius is proportional to the, inversely proportional to the applied external magnetic field. That means the radius of the skyrmions becomes zero only when we apply the magnetic field to which tends to the value of infinite. But here it's not the case. Here we can see that the radius of the skyrmions becomes zero at a finite value of magnetic field. So we could not consider this part. Now we talk about the skyrmions without DMI. That means we are considering other interaction which is responsible for this annihilation of these skyrmions. So if we talk about the Zeeman energy, which is responsible for the instability in the skyrmions, and if we talk about the dipole energy, which is responsible for the stability of these skyrmions, and if we apply the magnetic field, then the Zeeman energy exceeds a certain threshold value of dipole energy, and which could cause the annihilation of these skyrmions. So we have this relation through which we can calculate the critical value of magnetic field, which is around 0.3 Tesla. Now, interestingly, this value is very much closely matches with our experimental result, that is 0.32 Tesla. Hence, in this work, we have concluded that the skyrmions exist without DMI in bulk FGT. Now I would like to summarize my whole work. So initially we have prepared a spin polarized strip through which we were able to calculate, see the magnetic features, which are highly dependent on the applied magnetic field. And then we have go into the zoom in portion to the domain wall boundary level, and we found that there is no electronic state present at the domain wall boundary. And thereafter, we were able to quantify the value of domain wall width and the exchange stiffness. And finally, we have concluded that the bulk FGT hosts skyrmions without TMI. For more details, you could have a look at our recent publication in 2D materials. So in the last, I would like to thank everyone and every co-author of this work for their valuable contribution. Thank you very much for your kind attention.
Yeah, very nice talk, Namrata. I mean, very nice results. Can we have some questions? Yeah, so I see 2-3 questions by Nanhe Kumar Gupta. So the first question is, why 50 monolayer? Why not few nanometer?
Because we tried several attempts to it was not a one go where we found the spin polarized. If we go from the smaller value and then we reached up to a certain level where we found our out of plane magnetization. If we go beyond that, then our tip will become the in plane sensitive, where we can see the in plane magnetization. But in this work, we are able to see the out of plane magnetization only.
And the second question is, domain shrink means domain wall motion. Is it?
Yep. Yeah.
Okay. And one more question is, why have you calculated exchange stiffness constant, not exchange interaction? Well, this to me doesn't make sense, but yeah.
Yeah, I never think of it. So, what was the question?
The question is, why did you calculate exchange stiffness constant, not the exchange interaction? So one more question from our next speaker, maybe. I'm Raju. So what is the size of skyrmions in these samples?
So
Well, I think you have shown that slide, right? 262. Okay, that is the annihilation.
This is the smallest size. So
Yeah.
it was in the micron range. So the biggest size was in micron range, 1 micron meter.
So I have one more question related to this. So I mean, on which factors this annihilation field depends, basically?
So as I told that the DMI effect is almost cancelled in the bulk FTT. So if we consider other interactions like dipolar energy and the Zeeman energy, then if we apply the external magnetic field, which causes the increment of the Zeeman energy, and then Zeeman energies, as we know that they are responsible for the instability in the skyrmions, and if this exceed to a certain value of dipolar energy, then these skyrmions annihilates.
Okay. So there is one more question from Vincent Cross. What is the calculated exchange constant between layers? How different is it from interlayer one?
Exchange layers?
Yeah.
You mean this
what
one?
is the calculated exchange constant between layers?
This I
I think
don't know.
it is exchange stiffness constant, maybe, if I am right.
Yeah, this is from the DFT calculation. This you can see. Yeah.
Yeah.
It's
Yeah.
14.1.
So he's asking between layers.
This this I don't know actually.
Okay.
Sorry.
Okay. So I think we don't have any more questions. Okay. So if there is no more questions, then we can move to our next speaker. And thank you again for your nice talk, Namrata.